All right, so 10, 100, 1,000. Each time it's gone up by a magnitude of order of 1. So 10 to 100 is a magnitude of order 1 because we went from 1 to 2. If I was going to say 10 to 1,000, we'd say that's a magnitude of order 2 because I went from 1 to 3. And we're talking about really what power of 10 are you multiplying 10 to get to 1,000? You're multiplying by 100. So 10 squared. So we're talking about going up by orders of magnitudes. So that's a really slow growing function. Agreed? Would you agree that that's a slow growing function? Okay. Was there a question? A comment? No, we're looking for wipes. What are we doing? Oh, yeah, not in here. Down the end of the hall. You can go. I don't think it's a great sharpener though. Oh, but that's awesome.
A revolutionary idea for that.
Let's see. Thought we're back. All right, so a couple things about the graph. Up here. A couple things about the graph. So the graph of the log function looks like that. It crosses the axis at 1. So 1, 0 is a point on that graph. And this should look a little bit, or actually it should look a lot like, if you remember the 10 to the function, sort of the inverse of that. And again, it makes sense because they undo each other. The 10 to the function had the x-axis as an asymptote. The log function, so this is y equals 10 to the x. This is y equals log x. What sort of asymptote does log x have? Monty? The y-axis. And remember, when we were looking at like 10 to this was called a horizontal asymptote. And I think from last year from Algebra 2, you talked about vertical asymptotes, right? Okay, so let me just show you. I think you would remember. Here, I'll ask you the question. What's the limit as x approaches negative infinity of the 10 to the x function? So again, x is getting negatively big. What's happening to the value of the function? Mo, can you see it? It's definitely getting closer to 0. If you can't see it, you can actually plug in values that are very negatively big. So what we're saying is, look, as you're getting negatively big, what's happening to the function? The function is getting closer to the x-axis. Good. You can turn that question around and ask the same question about vertical asymptotes. And this is how I might ask the question for vertical asymptote. As x gets close to, let's say, 0, not infinity or negative infinity, what happens to the log of x function? So here we're saying, look, don't go out this way. Don't go out this way. Get close to 0. So what happens to this function when x gets close to 0? Now, if you can't see it, you can actually try something that's close to 0. You can't put 0 in because go ahead, try it. Try doing log of 0. Impossible. It is impossible. What does your calculator say? Error, domain. All right, it's telling you, look, it's not in the domain of the function. Look at that. Your calculator knows words like domain and range. I love it. Let's actually talk about that. Let's just take a look at this function. What is the domain of log of x? Danny?
All real numbers that are greater than 0.
All right, so all real numbers that are greater than 0. You can plug anything in that's positive, and you're fine. And there are lots of ways of saying it. I'm going to use interval notation. I'm going to say you can't plug 0 in, but you can plug anything from 0 up to infinity. Okay, and you can say that x is greater than 0. A lot of ways of saying it. What sort of values do I get out? And remember, this is where you want to look up and down, right? What sort of y values do I get out? What's my range? It's a little bit harder, but I think you might be able to see it. And if you don't see it, try looking at the table. Now, the table's going to be hard to look at, I think, because it goes up so slowly. I can understand that. Sam, you want to take a shot at it?
It's negative infinity to 1.
All right, so we
It
actually
never reaches 1.
we actually know that it does. Because what's the log of 100?
2.
Right, 10 raised to 2. So we actually know it does reach and goes past 1. So it's actually going to get bigger. I agree.
So negative infinity to infinity.
It is. And it's hard for you to believe. Why is it hard for you to believe?
Because after a while it pretty much goes straight almost.
Sam feels like this function is just growing so slowly that you just keep going out and it never gets bigger. Actually, the function always gets bigger. It just takes a very, very long time for it to get bigger. If you want the function to be a value of 100, you have to go out to 10 raised to the 100th power. Right? That's a lot of zeros after the 10. If you want the y value to be a million, you have to go out to 10 to the millionth power. That's huge. But however high you want the function to be, I can tell you what the x value is. It's just going to be a huge x value. All right, good. I totally got distracted. That wasn't the question we were asking. What is the limit as x gets close to 0 of this function? You just gave me some great answers. Evan, is that a hand?
Yep.
What do you want us to go with?
Negative infinity.
Yeah, here you are, walking closer and closer to 0. You're getting closer and closer to something that's negative infinity, right? It's huge. Travis, put it away. I don't know what you're doing tonight's homework. Put tonight's homework away. I don't know what you're doing. Can I I'm gonna add a little something to the notation which you may or may not understand why, and we can talk about it. I'm actually gonna put this little plus sign as a superscript for the 0. And that means we're getting close to 0 from the right-hand side. Do you understand how 0 plus might mean it's from the right-hand side a little bit more than 0? Right? You could imagine we could also use a notation like 0 with a minus coming at it from a little bit less than 0. Now, unfortunately, this would make a silly question to ask about the log of x because the function's not defined for less than 0. I could ask this, though. What does 10 to the x get close to when x gets closer and closer to 0 from the negative side? You can either look at the graph, you can think about it by plugging numbers in, you can look at a table. Corinne, thoughts or ideas? I'm not sure if it's a hand or not. No, definitely not. Sorry, I apologize. It looked like a hand. Travis? No, when x gets close to 0, that's like, look, you're on the, remember what function you're on. You're on the 10 to the x function. So that's saying, like, here you are, and here your friend is, and we're getting closer and closer to x equals 0. So you're getting closer here from the minus sign. This would be you getting closer from the plus sign. We're not worried about what we're doing. What does your friend think he or she's getting closer and closer to when x gets closer and closer to 0? I would say that does not look like infinity. 1? Keith says 1. Because, look, 10 to the 0 is 1, right? I would agree. And you can plug numbers in. There are lots of ways of looking at that. Evan?
How do you know what 0 you're talking about? Like the x or y?
Because this says when x gets close to 0, right? So think about numbers that are close to 0. Numbers that are close to 0 are like when x is negative 0.1, right? When x is negative 0.01, right? What is the y value? What is this getting closer to? It's getting close to 1. Okay? Does that work? Yes? Better now? Okay. All right, so look. Logarithms are really good for when you need to compare things that are magnitudes different. Like the distance of planets, right? One planet might be like something times 10 to the 12th. No, something times 10 to the, I don't even know, 29th, no, 53rd kilometers away. And another planet might be 10 to the 573rd kilometers or 1 billion kilometers or whatever. Those are such huge differences that logs are really good for comparing them. Like, it doesn't really make too much sense to say, oh, that planet's like 29 million kilometers further away. It might be easier to say, like, the difference of their distances in logarithms, it's like an order of magnitude of, like, 100 times further away. So instead of saying how many miles, saying it's 100 times further away might be helpful. Go ahead.
You would be talking about the distance between Venus and Mars?
Yes. I have no idea. All right, so what are logarithms good for? They're good for comparing things that are vast magnitudes different. And they're two very specific... What are you doing on your calculator? Are you spelling funny words?
No, I'm making really cool graphs with the logs and the
Well, good. All right, well...
I'm not even lying, too.
I believe you.
Michelle knows.
So here are the two things, one from chemistry and one from physics, that logs are good for. There are a host of other things. Have you guys done pH in chemistry? Okay. Yes? Yeah. Okay. So the pH is the concentration of hydrogen atoms in is it moles per liter? You got to help me out here because your chemistry is probably stronger than mine.
No, we're pretty sure this is 100%.
Yeah, no, all right. So the pH is the negative log of the hydrogen concentration, right? So this gives us a way of comparing acids and bases, right? Does this sound familiar? Yeah. Okay.
Oh, I remember that.
I hope you do because you've had chemistry more recently than I have. So if we were to take a look at a problem. Oops, I think I did the wrong symbol. Oh no, that's right. Okay, so if we want to find the hydrogen ion concentration, do a little work for me. Go ahead. I'm telling you what it's equal to, and I need you to find for me what that is. Go ahead, do a little work. I think you can set up an equation, calculate it, and let me know how many hydrogen ions, how many moles of hydrogen ions per liter we have. I think you can. Um, 4.5. That's acidic, right? Yeah, tomatoes are acidic, right? Okay. And neutral 7?
Yeah.
Is that true? Okay. So go ahead. What did you... Sure. Did you find something for me?
You have to make it exponential.
Yeah. Look, Danny's hint. If you don't like it in logarithmic form, change it to exponential form. Right? That's what you need to do.
Like Michelle. What?
So you've been throwing around words like pH, but now mathematically you know exactly what it means. And you know that it means a logarithmic relationship, but Danny's saying switch it to exponential. Tom, you want to set up the equation for me, and then we can look at it? Not quite, because this time we have the pH is equal to, we're given this relationship. Whatever the pH is negative log of the hydrogen concentration. Not yet. Just start with the first basic equation, and then I'll get there. I'm not ready for that yet. You're 2 steps ahead of me. of whatever the hydrogen concentration is. Okay, so Tom sets it up, and now I have to get it into exponential form. So Tom's told us what exponential form is. Dan gave us the hint. Max, you want to give it a shot at putting this into exponential form? Oh, please. What's the base? No, definitely not. Actually, the base is 10. That's definitely true. And as a matter of fact, I think maybe what I should do first is multiply both sides by a negative. I think I overlooked that. All right, so the base is 10, Andrea says. What's the exponent? Negative 4.5. And that's what the hydrogen ion concentration is. So 10 raised to the negative 4.5. And what's that, like point?
3.126 to the negative.
All right, so 0.00003, what? 316. So they're about 0.0000316 moles of hydrogen atoms per liter if you have in tomatoes. You could easily tell me what's neutral? Water? What? No, what is water? Distilled like water is neutral. So you could totally look at water, and can you see that nothing really would change except the exponent? So really it would just be the hydrogen concentrations 10 to the negative 7th. So that's 0.0000001 is the hydrogen ion concentration. So can you see that tomatoes have a whole lot more hydrogen atoms in it than water does? Not just like 1 or 2 more, but like orders of magnitude more. Like 1,000 times more. That's a lot more hydrogen ions, don't you think?
Yeah.
I think so. What?
To get the H alone, you divide by log, right?
You turn it into exponential, right? So 10 raised to the 7th is equal to, right? So those are important relationships to know. And to be able to go back and forth between logarithmic and exponential is huge. You have to know when and how to do it, without a doubt. All right. The next application is actually a lot harder, so I'm just putting it out there. And let's see. Tom, you're going to get to see this later this year. Any other physics fans in the room? Mo, you'll get to see it this year. All right. So, whoops. That's not what I wanted. Let's see. All right, so sound is another thing that we use logarithms to compare. And it's because the sound intensity or the sound loudness differs not by like 1 or 2 units, but by orders of magnitude. So the threshold of human hearing is like 10 to the negative 16th watts per meter squared. You don't have to worry about the units now, but it's like 10 to the negative 16th. That's what you can just barely hear. The threshold of pain, like something that would hurt your ear, would be like 1 or 2 watts per meter squared. So we're talking about a difference of 10 to the negative 16th, a teeny, teeny, tiny number, to a number like 1, which comparatively speaking is much bigger than 10 to the negative 16th, right? So we're talking orders of magnitude, and logs are great at comparing orders of magnitude. So, you may have heard of decibels, right? How loud a sound is, how many decibels it is. Is this true? All right. So decibels, and this is in your book, is equal to 10 times the log of the comparison of any 2 intensities. And so decibels is actually a relative measure. When we say, oh, it's 90 decibels in the cafeteria. It's like loud and boisterous. We're really actually saying it's 90 decibels more than the threshold of human hearing, what you can just barely hear. We never say, oh, it's 90 decibels louder than the threshold of human hearing. We just assume that that's what you say. But decibels mean we're comparing two sounds. So whenever you say decibels, it really should be louder than. So I could say like, hey, Mr. Capo's class is 10 decibels louder than my class. Right? It's a comparison. And we would be comparing those two sounds. So oftentimes, not always, but oftentimes, the sound that we compare it to is 10 to the negative 16th, because that's the threshold of human hearing.
Does threshold mean?
The lowest, like a threshold is something that you can't pass, so it's almost like a limit. So it's the limit of human hearing. If there's a sound that's softer or quieter than 10 to the negative 16th watts per meter squared, we will probably not hear it. Not all of us. There might be some of us that have really acute hearing, but we will probably not hear it because it's so soft. Okay. Michelle and then Elizabeth.
I was just going to ask about
Say again?
I was
Oh, I'm good. Okay. Elizabeth.
What if, so like say like there's a sound like I hear and some other people don't, does that mean that it's at that threshold or that it might be below and that I...
Well, so there are two, sounds is actually a pretty complicated thing. There are two things that could be going on. First of all, it's intensity, how loud or soft it is. So if it's less than that, it just might mean you have a more acute hearing. But there's also frequency of sound, and that's the pitch, like how low or how high. And many people have different ranges of pitch, and it's actually, there are studies that go to show that like adults, at the high end of the frequencies, we can't hear as high-pitched noises as you can. So I think there's like, every year there's something like, students set their cell phones to ring at frequencies higher than teachers can hear. So you can set your cell phone to go off at some like high-pitched thing that the adults in the room probably aren't going to hear. And that's true.
That's so cute.
Yeah. Go ahead, if you can figure it out. Yeah. All right, so here's what decibels shows us. So let me do a couple problems here. If a sound doubles, how many decibel ratings does it increase? Now you actually have two options. You can actually pick two intensities, right? One double the other. So I don't know. Do you want to pick two numbers? One that's bigger than twice as much as the other? We could pick 1 and 2. So we could actually do 1 over 10 to the negative 16th. All right, and how about this half of the room? You do that. And then the other half of the room, could you do 2 times 10 to the negative 16th? So you have to take the log of whatever the number is divided by the quantity, 10 raised to the negative 16th, and then multiply that by 10. Did you guys get what'd you get over here? 160? Okay. And what's this? I can't do this one in my head. 163? So if we compare these two, double the sound or double the loudness is an increase of 3 decibels. Right? And do you see how we just picked two numbers? This was Evan's strategy. Just pick two numbers, one that's double the other. Okay? Another way of doing that same problem would be this. What's if I take 2 and compare it to 1? Do you see how I'm comparing 2 to 1? I'm not comparing them both to the threshold of hearing. I'm comparing them to each other. So go ahead, do the log of 2 times 10. What do you get? 3? Okay? So, let me show you what these two things say. The first one says, a sound intensity of 1 is 160 decibels. A sound intensity of 2 is 163 decibels, so the one that's twice as loud is 3 decibels more. I can combine them into one equation and say the comparison of sound intensity of 2 to 1 is 3 decibels, meaning that a sound intensity of 2 is 3 decibels more than 1. Do you see how they both give you the same information in a different way? Is that all right? Sound intensity and decibels is a little more complicated than the pH problems. The pH problems are a little more straightforward. The sound intensity problems can be a little more challenging, okay? Because there's usually more than one way of setting up the equation. Elizabeth and Evan, maybe? Were there a couple questions? No? Evan? No? Oh, okay. Good. That's a good thing. We should all have good hair. All right, so, look, I owe you from last night, right? There were a couple word problems. I know 51 had questions. Can you give me an idea? Other ones other than 51, were there a lot that were hard or just like...
Well, I don't know about the even numbers.
Yeah, even
I was 34, 29.
Okay, so it sounds to me like there were some that went well, but there were some that definitely you're not sure about. Is that true? Okay, so here's how I see it. Have a great long weekend. On Monday, we'll regroup. We'll talk about logs. We'll talk about the word problems. We'll work on tools. On Tuesday, we'll go over tools and start reviewing. On Wednesday, we'll finish up our review, and I think that puts us in a good shape to take a test Thursday. And then I'll be able to give you the project on Friday. I'll miss you terribly.